Okay, we're going on now to Chapter 8, and we're dealing with sample space, events, and probability. And it starts actually on page 372. There's an introduction where they talk about some mathematicians back in the 15 and 16 centuries who were actually gambling. And from thinking about the things they were doing in gambling, they wondered if it was connected to math, and they actually found that it was. And it's given rise to this concept of probability. So if you want to read that, again, you're welcome to do that. And then it goes on to say on page 373 that what we had learned in the previous chapters on union, intersection, and complement of sets will be something that we will need to bring in to problems when we start looking at specific examples. We want to define some terms. A random experiment almost sounds like science here. Well, it is a science. What does it mean to be random? Well, it means it's going to be sort of mixed up in no particular order. Random, like a deck of cards that is shuffled in a really good way, as opposed to having them all set up in suits or by their card identity. So we use this concept of a random experiment. Now, in some cases when you gamble, if the table you're gambling on is set in such a way that they may limit the freedom of things, then we say the fix is in. Again, I don't know too much about this, but we're hoping that most things should all be random and not fixed. And what are we talking about? In common things, coins. If you flip a coin, are you going to get a head or a tail? There's two sides of a coin. If you're going to pick a card, a particular card out of a deck of 52, that would be the random event. Now the deck has to be an honest deck, again, to make it random. And when you throw dice, each dice is a cube or die, and it has 6 sides. And again, there's 2 of them. So we'll be talking about that in some detail. But if the die is not a real true die, one side has been weighted, so one side comes up more frequently, we say those are, again, I'm not too sure of the word, but they're fixed, and they're not a true die. So then we talk about our sample space. What is our sample space? Well, for coins, there would be 2 sides, a head and a tail. So our sample space is 2. And then the event that you're looking for. What event? Well, do you want a head, for instance? That would be your event. And for cards, that you want an ace of spades. That's 1 out of 52. That would be the event you're looking for. Or you're looking for a 1 on one die and a 1 on the other. I know that is called snake eyes. And then a 6 on one and a 6 on the other, that's called boxcars. I remember that from somewhere. I don't play with them too often, but that's what they're talking about. So sample space, the possible outcomes that can occur, and then the event, the specific event you're looking for. Sometimes it could be a simple event or a compound event. A simple event would be one ace of spades out of a deck of cards. A compound event would be an ace out of a deck of cards. So it's not just one thing, but a possibility of more than one. Okay, that's the first part. Okay, now in example one of the things they talked about that we didn't mention is they have a wheel with the numbers that they can actually spin, and then some kind of pointer, like the Wheel of Fortune. You've all seen that. And that is our sample space. And now we're looking for an event, and here our outcome is a prime number. So out of 1 through 18, as our possibilities, what would be our prime number? Well, you start to list them. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there's our set of prime numbers in our wheel of 18 numbers. So our sample area would be 1 of 18, and the event would be these numbers here. So what type of event would this be? Well, they're looking for a compound event. Because it's made up of more than one element. In part B of example 1, they're talking about the outcome is the square of 4. So what is the square of 4? Well, it's 16. There's only one element there, so this is a simple event. Going on to example 2, and by the way, the other one was on page 74. This is on page 375. Here we are tossing together a nickel and a dime. And we're wondering what the outcome. We're trying to figure out what is our sample space. And this is not quite the way they do it in our textbook, but from my biology background, this is the way we might do it there, where we're talking about genetics a little bit. So there's our dime, our heads and the tails. There's our nickel, our heads and tails. And what we want to do is see what our possible results are. Well, here, if we feed that into there, we get an HH. Here we get a HT. Here we get a TH. And here we get a TT. So our possible outcome, our sample space, there are 4 items. And we might say, what is the event we are looking for? Well, let's say we're looking for a heads. Okay? Now, if we're looking for a heads, we get one of those. If we're looking for a heads or tails, remember that we get 2 of those. And if we're looking for a tail, we get 1 of those. In fact, just tying it into biology a little bit, you might recall that this is a 1 to 2 to 1 ratio if these were like intermediate traits or something. But again, we're looking for, in this area, sample space, 4 items, and then the items that we're looking for. Okay, in example 3, and I'm on page 76. This is sample events in space, but relating to dice. And this is something you're going to need to know. And in the textbook, they have a chart of this as well, right there in the central area. And what I did is made the 6 die along this row, 6 die along this column. So if you roll this, you would get a 2, this and this a 3, 4, 5, 6, 7. And these are all the possible combinations. Now, how many possible combinations can you have when you roll dice? Well, this has 6 sides, and this has 6 sides. So if you counted all of this, 6 times 6, there are 36 possibilities out here. Now, if you look at the number, how many times is a 2 there? Well, just once. How many times is a 12 there? Just once. So let me show you a little trick that if on your test day, and they're asking you about dice, and you don't remember all the details, you can quickly duplicate this. That you're going to start with the first number you can get when you roll 2 dice. The smallest is a 2, and the largest is a 12. And then the possible combinations that are found on this little board summarized is you get a 1, 2, 2 3s, 3 4s, 4 different 5s, 5 different 6s, 6 different 7s on a die, set of dice, and then the numbers start going down again. So 1 on either top, 7 has 6, which is the highest number, and then 1 through 5, and then coming up 1 through 5 with 6 in the middle. Now, a little later, I can perhaps, getting ahead of myself a little bit, but what then would be the probability of rolling, and we get into this in the next section, but while I have this here, let's say a 7. Now there's 6 different ways to make a 7. So that would be then, the event you're looking for is compounded at 6. That's the number of times you could possibly get a 7 out of 36. That is your sample space, and then that's reduced to 1 out of 6. So the probability of rolling a 7 when you roll dice, that's your greatest chance. 1 out of 6. 6 out of 36. Now, what's your probability of rolling, let's say, snake eyes, which is a 1 and a 1? And the answer is there's 1 out of 36. That's a very hard one to get. How about a 12, which is called freight cars? Something like that. Anyway, again, I don't play dice, so I don't know this too much. 1 out of 36. So any of these numbers is 1 out of 36. But notice the 7s are repeated right in here. 8s are repeated here. A couple of good things going on that if you're not familiar with dice, this is a good little item of review. And before I erased the board, I was showing this to a colleague, and they pointed out, too, that you could see it this way. There's the possible outcome of a 2. There's 1 there. Possible outcome of a 12. There's 1 there. And then in 3s, there's 2. 11, there's 2. 4, there's 3. 5, there's 4. 6, there's 5. And there's 7 is 6. And then 5, 4, 3, 2, 1 again. So again, a good little study aid there, and something that can be reproduced. You can't bring notes into a test, but if you can remember this, this is a good little aid. Going on now to example 4 on page 378, the probability of an event. That in general, the probability of an event is a ratio between the specific event you're looking for, that is the interested item, out of the sample space. So in example 4, they're using the dimes and nickels, where the number of, forgot to put an H there, here we go, of results. There are 4 possible results, and this occurs 1/4 of the time, 1/4 of the time, 1/4, 1/4. And notice that these 2 events are, for all practical purposes, the same, if order's not important, which it isn't here. So this gives you the 1/2. And if you recall before, I had mentioned the ratio of 1 of these to 2 of these to 1 of those. This was a dihybrid cross of what we call intermediate genes or something. Okay. Now, what's the probability of getting a heads and tails? And again, it's 1/2 because there are 2 possibilities. Getting 2 heads, 1/4. 2 tails, 1/4. And we would just add these together if we wanted other combinations. Now, an interesting point they bring up is, what is the probability of getting 3 heads? You might say, well, wait a minute, there aren't 3 heads there. That's right. So the probability of 3 heads would be an empty set. There is no probability. All right, in example 5, on page 380, 381, they're talking about equal probability, where an event, in the sense of dice, that you end up with a sum of 70. I'm sorry, a sum of 7. Now remember, your field is 36 for all of these. That is your sample space. What's the probability of getting a 7? Well, we said there were 6 ways, looking at that chart, of getting a 7. How many ways of getting a 4? Well, there were 3. Of getting an 11, there were 2 ways. To get a boxcars, not freight cars, boxcars, there's just 1 way. Now, in each of these examples, we can see that these fractions can be reduced. And in order to give our answer correctly, they must be reduced. So this becomes 1 out of 6. This is 1 out of 12. This is 1 out of 18. And this is in its lowest form. And that would be example 5. Now, keep in mind, in your textbook, there's a lot more information about this. What I'm doing is just reviewing it and giving you some pointers. All right, we're going to jump to example 7 on page 382. And we're getting back to our deck of cards. But then they say we're going to draw 5 cards from this deck. What is the possibility that we're drawing 5 spades? Okay? So actually this is one that I referred to before, in which it's going to be a ratio of the event we're looking for out of our sample space. And it's a combination problem. So the combination of, there are 13 spades in a deck, and we're interested in 5 of those spades. And then there are 52 cards in a deck, and we're interested in 5 of those cards. So it's a ratio. This is going back to probability. And let's set the first one up. So C13 comma 5 is 13 factorial. Our R is 5 factorial. Then N minus R factorial over 52 factorial. R is 5 factorial. 52 minus 5 factorial. And keep in mind, this is a complex division of fractions problem. And what did we say earlier when we did this? Well, it's this divided by this. I've simplified it here a little bit. And then this is divided by this. And what we do is we change this from division here to multiplication, where we take this and flip it. So the 52 now goes on the bottom. The 5 and the 47 go up on top. And that's what we have. Now notice, if you were doing this mathematically, you could put all of that into your calculator. Or, since we have 5 factorial here and 5 factorial there, we could cancel that out. And remember, we did something like that. But again, since you're using a calculator, just put it in like that. And put the top in, divided by, put that in parentheses now, and that will give you your answer. And it's quite a big answer here. Well, actually, this one is a small one, and it's approximately 0.005. Do I have enough zeros there? No, I have to add one more 0 there. There we go. So 5 10,000ths. Again, the odds of doing that are pretty slim, but there is a probability. While we go over this probability thing, I think any of you who stay up late in the evenings and watch the lottery numbers coming up on TV, you see they have a series of digits and they're being blown by air, and that moves them around, and then they release something and one randomly pops up. So there you're seeing what is called randomness in action. In flipping a coin, some people can get so good at it, they can put a head here, and every time, depending on the strength of the toss, they could figure out what it is. So that's not an honest toss. That's the fixes in there. So with that, we'll say this is our review of sample space, events, and probability. We have 2 more topics to do before we complete our video program of Math 1127.